Great. Good day, everyone who's come to this public lecture. CIMTR are very pleased to give a warm welcome to John Stuart Reid, who is going to give us a talk on Cymatics, the study of visible sound. His Cymascope invention has changed our perception of sound forever. Seeing sounds allows us to understand this omnipresent aspect of our world and universe fuller and deeper. His Cymatics research is helping to elevate this important new field in the scientific arena, including a study on how dolphins see with sound, which is published in the Journal of Marine Biology. And also in the Water Journal, there's going to be a paper on cymatically differentiating between the sounds emitted by healthy cells and cancer cells. In 2021, John was invited to write a chapter on sound therapy and music medicine for a new medical textbook, which was published in 2022. So there's a lot of great recent research coming out, and that's published in English, Russian, and Slovak. And a free e-copy is available via the breaking news section of his website, which I will put a link to in the chat now. So, John, a very warm welcome to you.
Thank you so much for the lovely introduction. So my career actually spans, well, 5 decades. And for the first, 2.5 decades, I think, I was an acoustics engineer and I ran my own acoustics consultancy business. And then I had an experience in the Great Pyramid, which really changed my entire life. Following this particular experience in which my lower back was miraculously healed from a very, very severe, painful injury within 20 minutes of making sound. And whereas no amount of analgesic pills that I had taken leading up to my visit to Egypt, this particular visit, had touched that pain. And I had also visited a physiotherapist. That didn't work either. And yet 20 minutes of sound in the King's Chamber, during which, it also was an astonishing experience because I was seeing ancient Egyptian hieroglyphs pop out in sand sprinkled on a membrane stretched across the open top of the sarcophagus. So you can imagine that I was excited, anyone would be seeing these ancient Egyptian hieroglyphs cymatically created by sound, exciting the quartz crystal matrix of that granite. So obviously I thought, I know what's happening here, why the pain is muted or mediated is because my bloodstream is flowing with endorphins naturally because of the excitement and so on, but actually the pain never came back. So later in this presentation, we'll get to the point of explaining why that pain was literally banished for good. Anyway, I'm going to start screen sharing now. So this presentation concerns mainly the sound therapy and music medicine biological mechanisms. And this particular slide that you're looking at here, which of course is just a graphic depiction, it's showing cells and it's showing a sound field actually moving through this cellular material and then a pattern of energy imprinting onto that cell membrane. We come back to that whole idea a little bit later. As Alex was saying, there's a new medical textbook that's been published with this very catchy title, A Comprehensive Multi-Professional Approach to the Treatment of Patients, focusing on the use of less frequent methods. And it's the brainchild of Dr. Gustav Solar. My chapter in that textbook is focused on sound therapy and music medicine. I definitely encourage you to download an e-copy of that book. It's really a fascinating book. And the chapter that I wrote is very, very well referenced, so it would give you a lot of material to work with. Let's begin with a brief introduction to Cymatics. And essentially, it's the study of visible sound. Many people ask me, what is the difference between a Cymascope instrument, which you see, by the way, right behind me here, and a Chladni plate? So first of all, just let me say that because of that amazing experience that I had in 1997 in the Great Pyramid, that really set me on this path that I'm still on today, now as an acoustic physics scientist rather than engineer. And two things really, two directions in my life. One has been to develop this new instrument, which is now in use in university departments and private research institutes all over the world. But also, of course, to discover that biological mechanism that had banished the pain and all of the other wonderful mechanisms that are at work in our body whenever we are immersed in a musical environment or in specific sound frequencies. So coming back to this idea of what is the difference between a Cymascope instrument and a Chladni plate, in essence, you see there on the right-hand side an old drawing of a Chladni plate in use. Of course, this is named after Ernst Chladni, the famous German physicist and musician, who experimented with this whole idea. It actually originated with the famous English scientist Robert Hooke, much earlier than Chladni. But anyway, it's Chladni who's gone down in history as being famous for experimenting with this plate. And essentially, what you need to know is that when you play a Chladni plate with a violin bow like that, then you're going to be exciting many different resonant modes, resonant frequencies of that plate. So these are the natural inherent frequencies, vibrational frequencies of the plate. So you're going to see a beautiful pattern emerge at different, wherever you play that plate, at different sides, different positions rather on the edge of the plate. And how much friction you use, of course, also determines the note that will be played. But the point about all of this is that you're not really seeing sound made visible mainly. What you're mainly seeing are the resonant properties of the plate made visible. Now, obviously, there are mathematics describing how this plate creates these patterns, but essentially the idea that you can make visible a sound pattern is a little bit of a stretch, because really, primarily, these modal patterns are really strongly dominating what you will see. However, on the left-hand side, you see the Cymascope instrument. The difference is, first of all, that we use pure water as the imaging medium, not sand or salt on a plate. So we're using pure water. Now, of course, the various elements of the Cymascope instrument also have natural resonant frequencies, but we tune them out electronically. First, we identify them with an accelerometer system, then we tune them out so that whatever sound you put in, it basically creates an accurate geometric model or analog of that sound made visible. And that's the fundamental difference. Coming on now to the holographic properties of sound, you may not have realized that sound is holographic or quasi-holographic, but indeed it is. I just want you to have a little look at this beautiful seven-fold cymaglyph. This is the word that we use to describe a sound image. That's the voice of a dear friend and colleague, Jonathan Goldman, made visible with the Cymascope instrument. And when you study this image, you'll see that it is indeed quasi-holographic. It has multiple layers to it. And the reason for this is because when sound enters into water, it organizes the trillions and trillions of water molecules in a blink of an eye, a tiny fraction, a few milliseconds basically. And all of those molecules are beautifully organized, and not only on the surface of the water, but right into the depths of the water. And this, of course, infers that whenever you're immersed in a musical environment, for example, that the visceral waters in your body are also going to be beautifully organized. We're coming on now to a video that actually shows you this principle. In this case, it's a Cymascope video, but we're using a cubic cuvette, or certainly a square section cuvette, and you can see it's partly filled with water. This is obviously a still image. You can also see at the right and left-hand sides what we were all taught in school all those years ago about capillary attraction. Of course, it's not really it's not really an explanation for what's happening. Why is the water climbing up the walls of the tube? Well, we'll come to that a little bit later in this presentation, but suffice to say that you're seeing there the datum of the water's surface. I'm now going to switch to a video, and you're going to see this literally the water being excited by a 10 hertz sinusoidal frequency going into that water, sonic frequency, and then just watch what happens. Cymascope cubic cuvette experiment number 3. This time we've lowered the level of the water so that we can see more detail both above and below the level of the water. So bringing up the amplitude slowly, still have 10 hertz excitation frequency. We have structure beneath the surface that seems to be without any structure above at this time. Bringing the amplitude up further. Again, from this perspective, the structure all seems to be beneath the surface. Okay, so I now need to show you what that looks like from above, but the essence of this is that if we had kept on increasing the amplitude, then of course eventually there would have been an excursion above the water's surface, but all of the organization that's happening at this particular amplitude is happening beneath the water's surface. And now have a look at what you're seeing from above. And now you see a really beautiful cymaglyph, as we call it, in this case a square section cymaglyph, but all of that beautiful organization is happening because of that simple 10 hertz sinusoidal frequency. This is another video. In this case, this is a microscope slide, and here it's a Teflon coated slide, and I've basically squirted it with some microscopic droplets using a perfume atomizer, actually. So this is pure water. Some of these, the two largest droplets are maybe just a little bit larger than typical human cells. Some of the smallest droplets are actually smaller than human cells. But the point of this is it's kind of a precursor piece of research before I move on to actually image sound literally and music indeed on the surface of living cells. It's very instructional when you watch this video. So let me just play this video for you now. Let me just stop it there for a moment so you can see what's happening. The two largest droplets are exhibiting a rather beautiful cymatic pattern, whereas the medium-sized droplets, when I play it just for another second or two, you'll notice that they are trying to do something. They're obviously absorbing some of the energy, the acoustic energy, whereas the smallest droplets, this is rather like the Three Bears illustration, isn't it? The smallest droplets are doing nothing at all. It's apparently they're ignoring the acoustic energy. Let's just play it for another second or two. And why is that? Well, obviously it's due to resonance. So even in the microscopic scale here, you see the importance of resonance. So the largest droplets are obviously very much in resonance with this particular sound that's coming in. The medium-sized droplets, well, they're starting to react, but they're not creating a cymatic pattern yet. Obviously, if I had increased the amplitude, eventually they would have. And then the smallest droplets are apparently completely ignoring it. So this is very important from a point of view of resonance in terms of how sound and music literally is absorbed by the cells of our body. And there is a very close-up graphic showing you the integral membrane proteins that are projecting from the cell membrane. And one of the mechanisms that I talk about, I won't go into great detail today, but one of the mechanisms concerns the G0 phase of the cell cycle. You know, when a system in your body is challenged by an invasion of a pathogen or perhaps imbibing some toxic substances or whatever, it could be physical trauma, the system can go to sleep. It goes into a kind of cellular sleep phase called the G0 phase of the cell cycle. And when sound frequencies penetrate into your body, they can literally act as a form of sonic nutrition, which reawakens the cells, encouraging them to rejoin the cell cycle. And these cymatic principles that I'm referring to happen regardless of scale. You might know about this as a giant hexagon on the north pole of the planet Saturn, which is so large it could swallow 3 Earths. And hypothetically, it's created by low frequency sound from a geyser or a geyser emerging up into the upper layers of the atmosphere. And then, of course, literally they travel outward. Now, normally with any kind of cymatic principle, there has to be a boundary condition. And indeed, in this case, there is a boundary condition. It's a storm traveling at about 1,000 miles an hour that forms a kind of palisade. So the energy then reflects back to the epicenter. Now, this is a hypothesis, of course, and you can study this later because we will be sharing these slides with you. So I'll just move on now. Cymatics is a triadic phenomenon. What this means is that the frequency of excitation generates the dynamic standing wave, which in turn creates the apparent stationary form, in other words, the cymaglyph, as we call it, the sound image. But in reality, cymaglyphs only present an illusion of permanence. Their genesis can be studied during different phases of oscillation, for example, when viewed by means of a camera, if you then select different shutter speeds. And it was Sir Humphrey Davy who said, "Nothing tends so much to the advancement of knowledge as the application of a new instrument." And how right he was. What would we know about the realm of stars without a telescope? Well, very, very little, actually, when you think about it. What would we know about the realm of cells without a microscope? Well, even less, because before the invention of the microscope, no one even suspected that such a realm existed. And what would we know about the realm of visible sound without a Cymascope instrument? And again, the answer is extremely little. So the Cymascope instrument images a cross-section through the sonic bubble. And here you see a violin, a young violinist playing this beautiful note, and a beautiful sound bubble is emerging from her violin, frozen at a moment in time. In the center part of the graphic, you see the bubble has been halved, and on the right-hand side, you see the cross-section through that bubble. There's a larger image of it. And from the holographic point of view, it basically means if you could zoom in to any atom or any molecule on the surface, the notional surface of that bubble in this frozen moment, and look at the vibrational spectra of that atom or molecule, you would see that it contains all of the vibrational information relating to that particular note that that young woman is playing on her instrument. Now, if you were to zoom into any atom or molecule on the interior of the bubble, likewise, you would see exactly the same vibrational information. It doesn't take a whole bunch of atoms or molecules to actually show us the vibrational information. It's all contained in a single atom or a single molecule. And this is why we can say with confidence that sound is holographic or quasi-holographic. And there's a very nice illustration of this very strange situation we find ourselves in, where everyone's talking about sound waves that don't literally exist in nature. You know, if you ask anyone, you know, what is the shape of sound, they will always tell you it's a wave. But if you then say, well, show me that wave coming out of your mouth right now as you're talking to me, they will literally show you a wave wiggling its way through the air. And of course, that is so untrue. It's literally a bubble, a sonic bubble that's emerging from that person's mouth and nose. There's the illustration showing you where this term wave comes from. It literally comes from the compressions and rarefactions of the vibrations in the sound bubble, but shown graphically. But of course, nature does not use graphs. Coming on now to the very brief introduction to the physics of sound, which is actually extremely important in relation to sound therapy and music medicine. Why? Because sound gives birth to infrared light. And this little graphic is showing you why that happens. Around all atoms and all molecules, there is a magnetic shell, you can call it, a magnetic moment, it's usually termed in science. And when two atoms or two molecules collide, of course, it's the magnetic moments of these atoms that are colliding with each other. And in physics, we call this an inelastic collision. Of course, in relation to sound, it's an inelastic sonic collision. And whenever two atoms or two molecules collide, first of all, they do share their vibrational information with each other. But the other thing that happens is that light is created, always, with any sonic inelastic collision. And the light that's created, mainly on this Earth, it's created in the infrared spectrum. Of course, it's quite possible to create visible light with sound, for example, sonobioluminescence, and also some of the actual metabolic processes going on in your cells, even there, create some visible biophotons, very little, but some, but mostly it's infrared light that is created. And it's very important to know that the light that is so created by sound and by music is modulated in frequency by the music or by the sound. And of course, we know this is true. One of the simple ways to know that this is so true is simply by rubbing your hands together. And if you rub your hands together very vigorously, you know that it will create warmth. And we use this everyday term friction to describe what we're doing. It's the friction between the molecules or the proteins, let's say, in the skin of one hand, rubbing past the proteins in your other hand. But really, at the atomic level, it comes back to these magnetic shells around the atoms and molecules that are slipping past each other and creating radiant radiation, basically, which in this case is in the infrared spectrum. And I like to say it simply, sound gives birth to light. And here is the formula that actually shows you why this is true. It's very simply written as PVA, where P is the sound intensity and the particle velocity is V and the surface area is A. And this actually may explain why a gentle caress of the skin feels like electricity, because in theory, such low particle velocities actually create low-level microwave energy. And it's also why all sounds create either infrared light or, in some cases, as I mentioned, visible light, e.g. biophotons. And when we sing to the stars, if we go outside and sing literally to the stars like Julie Andrew on the top of a hill, the sound of music, the atomic inelastic collisions created by our singing create infrared light that is modulated by our voice frequencies. And that IR light zips through the atmosphere into space, where theory tells us it will travel forever unless it meets some dense matter. And of course, I'm sure you all know about the James Webb Space Telescope, which is optimized for infrared wavelengths. So perhaps at some future time, the James Webb Telescope will be able to literally listen in to the sounds of exoplanets, or perhaps there's an ocean with waves crashing on the shore, and therefore it will be perhaps sensitive enough to pick up that ocean, those ocean waves, not of course in sound, but in infrared light modulated by the sound. But even today, the science of asteroseismology is using the same principle that I've just related, where the sounds inside stars, in the furnace of the stars, create tiny fluctuations in the starlight that's then picked up by a powerful telescope, demodulated, and turned back into sound, so that the asteroseismologists can study what's happening inside the star. And of course, in the Buddhist tradition, they believe that when striking their giant temple bell, the sound reverberates throughout the universe. And we now know that they are actually correct. though the sound of the bell actually propagates into space as amplitude modulated infrared light. And why is this important? Well, it's important because intercellular communication occurs mainly in the far infrared spectrum. The physics of sound-light interactions infers that sonic modulated light is conveyed to cells in the medium of their own language, and that music and other therapeutic sonic frequencies convey harmonic energy information direct to the cells. And here's a very nice graphic from a paper that I'm just about to share with you, showing where that cell-to-cell communication occurs, what part of the frequency spectrum. A little bit invisible and a little bit in UV, but most of it occurs in the IR spectrum. And there is the actual paper. I highly recommend it. It's a really wonderful read by Gemma Reguera. We're coming on now to structured water. You know, I mentioned much earlier there about that cubic cuvette and why the water climbs up the walls. Well, of course, we now know that this is all due to atomic attraction, and that kind of water at the boundary of any glass, or in this case, the cubic cuvette of the Cymascope instrument, or the circular section Cymascope cuvette. In both cases, or all these cases, we're talking about water which has changed its atomic structure to H3O2, and this gives it very specific electrical properties, and this is why the water climbs up the wall of the glass. But also, very importantly here, there's a connection waiting to be explored between sound frequencies that organize water molecules and EZ water, exclusion zone water, that powers life. And Dr. Pollack has discovered that EZ water is built by light, particularly infrared light, yielding a potentially fascinating connection between sound and our physiology, which is this: inelastic sonic collisions create sonically modulated infrared light that powers the EZ water building mechanism in cells, which in turn powers our biology. Isn't that beautiful? And so, put simply, sound powers life. Coming on now to the phi ratio. All harmonic sounds contain phi, the golden ratio. I'm sure you all know that, 1 to 1.618. And since this important ratio is prevalent in the DNA of all living creatures and in the proportions of their forms, it can be stated that there is a natural connection between sound and life. And here are some of the many formulas that show the relationship between harmonic sinusoidal sound and the phi ratio. And here's a cross-section through the DNA molecule revealing its tenfold structure. And since 5 and 10-fold structures contain phi, the golden ratio, we can correlate the structure of DNA with the sine curve, as shown in the various formulae linking phi with sound. Excuse me. Pentagonal geometry, of course, contains the golden ratio and is deeply embedded in the DNA molecule, as I've just shown you, but also in every sinusoidal sound. So when the pentagon is phase shifted by 45 degrees, tenfold geometry is created, exactly as occurs in the cross-sectional structure of the DNA molecule. This is also extremely interesting by a colleague of mine, Professor Petukov, the importance of the 3:2 musical ratio in vocalizations has come to light as a result of discoveries made by this Russian team led by Sergei Petukov. And apart from the commonly known aspects of this ratio, it is less well known that it also exists between the frequencies of the second and third harmonics of any oscillating string, and of course by our vocal folds, and in any harmonic sound. Professor Petukov and his team discovered that complementary pairs of nitrogenous bases exist that feature 3 and 2 hydrogen bonds respectively. DNA is therefore a chain of numbers 3 and 2 of the hydrogen bonds, and the implications of this discovery are that when we sing or immerse our body in harmonic sounds, we are actually singing a form of genetic music, music that brings healing to all life. And here are some wonderful illustrations from Georgi Doski's beautiful book, The Power of Limits, who elegantly reveals the phi ratio embedded in all human, animal, insect, and plant life. We're coming on now to sonocytology. This was a word coined by Professor Dr. James Jimzewski and his team, UCLA. And what they discovered is that all cells sing a song. Well, they're using this term poetically, of course, but in reality, the metabolic processes that are going on inside cells all of the time cause a kind of respiration of the cell membrane. In other words, the cell is physically moving and creating sound. And interestingly, all of the frequencies generated by human cells are created in the audible spectrum. That's not to say that we can literally hear them, but if we had ears sensitive enough, yes, indeed, we would be able to hear the sounds of our own cells, and perhaps it's just as well that we cannot. Anyway, in this little slide here, you're seeing the actual principle by which Dr. Jimzewski originated this science. So it's using an atomic force microscopic method, and of course, it's simply a stylus, a little cantilever that literally rests on the cell membrane, and then as the cell membrane respirates, makes its sounds, then a little laser beam literally reflects off it and takes the light to a diode, a photodiode. And this is a quote from Dr. Pelling's article. He was an assistant at that time to James Jimzewski, and he said this: observing cells in different situations, for example, cells under stress, generates different sounds. In fact, the state of the cell, if it's healthy or cancerous, can be distinguished by listening to its sound. In future, we hope to bring our research in sonocytology to the point at which it can be integrated in medical disciplines such as cancer research. Listening to cells would allow a fast diagnosis of cancer without the use of drugs or surgery. Sonocytology might also make cancer detection possible before a tumor forms. And Professor Sungchul Ji and I used exactly that method, or very similar method, to detect the sounds of cancer cells and healthy cells, and then make them visible with the Cymascope instrument. Actually, we didn't use atomic force microscopy. In this case, we used Raman spectroscopy, which is actually much simpler, easier to use system than AFM. And this was one of the results that I'm showing you now. This is a typical cymaglyph from a healthy cell on the left, and a typical cymaglyph from a cancerous cell on the right. And you can see very obviously that the healthy cell produces a, well, quite beautiful image, actually, very symmetrical, whereas the cymaglyph of the cancer cell is by comparison rather ugly and skewed. And there is the paper that we published in the Water Journal on this research. We're coming now to the kind of meat of this presentation: how sound and music supports healing. First, the role of nitric oxide. Nitric oxide reduces blood pressure by vasodilation, and many other health benefits are derived from this important molecule. For example, promotion of wound healing by cellular proliferation and angiogenesis, mediation of cutaneous edema and inflammation, cytotoxic action against pathogens. It increases cerebral blood flow and oxygenation to the brain. It inhibits the aggregation of platelets within blood vessels, thus helping prevent thrombotic events. It supports reduction of pulmonary hypertension and chronic obstructive airway disease, and much more. So this is a very, very important molecule in the body. And in this paper that I'm mentioning here, assessment of nasal and sinus nitric oxide output using a single breath humming, they actually showed that a single breath can cause this remarkable increase in nitric oxide levels. You need to know that nitric oxide is produced in the paranasal sinus cavities and in the lungs. In the paranasal sinus cavities, the Helmholtz resonant frequencies are between 1 kilohertz and 2 kilohertz, depending on skull size. And of course, whether you're male or female, typically females tend to have slightly smaller skulls, males tend to have slightly larger heads. Anyway, nasal breathing increases nitric oxide production and can be enhanced by active humming and singing, and passively, this is important, passively by full body immersion in music. Nitric oxide is also produced in the lungs, which have Helmholtz resonant frequencies of between 100 hertz and 150 hertz, again, depending on male, female, body size, and so on. But this aspect of passive, I think, is extremely important, because it means that whenever we are immersed, full body immersion in music, then because of Helmholtz resonant properties, then it means that the paranasal sinus cavities and the lungs are going to generate nitric oxide automatically for us. And there is the frequency for the calculation formula for Helmholtz resonance for those of you who are interested in this. How does music boost the immune system? Well, a lot of writing on this slide. You can read all of this later when you review these slides. But essentially, music played live to patients via speakers, again, I'm talking about full body immersion, in a myriad of sonic frequencies that have both physiological and psychological benefits. Music can, of course, evoke happy memories of times, places, or life events that can quickly transform a patient's mood into a sense of joy, in which state the brain and enteric nervous system in the digestive tract produces dopamine, which boosts leukocyte production in the immune system. And in parallel with this increase in dopamine level, a patient's favorite music also causes a reduction in cortisol levels. Very important in both cases. And so I encourage you to read these notes later. We're coming on now to mediation of chronic pain by sound and music. Chronic pain, of course, is a common, complex, and distressing problem and has significant impact on individuals and society as a whole. Chronic pain, like most diseases, often arises from a series or a combination of multiple events. The biological processes that lead to the chronic pain state further increase sensitivity to painful stimuli and perceived levels of stress, and this further modifies pain-related gene expression, therefore creating a pathological pain cycle. Prolonged use of analgesics, such as chronic opioid therapy, is associated with constipation, sleep-disordered breathing, hypothalamic pituitary adrenal dysregulation, fractures as a result of osteoporosis, and significant declines in health-related quality of life and increased healthcare costs. I don't know why I'm laughing here. I mean, the point is that chronic opioid use is very, very bad for people, and this is why it would be advantageous to mitigate chronic pain without long-term use of analgesics. And according to research by the Niels Bohr Institute, the nervous system of the body primarily conducts sound, known as soliton impulses, which in turn create electrical impulses via the piezoelectric effect. This is an astonishing discovery, and it has such huge implications for your field and indeed for mine. All categories of nerve fiber are sensitive to mechanical vibration, that is, specific sound frequencies and music. And there you see the different diameters of the various nerve categories. Again, a very busy slide, which I'm not going to read, concerning the gate control theory of pain, first proposed in 1965 by Ronald Melzack and Patrick Wall. And this theory was initially met with considerable skepticism, but despite having to undergo several modifications, its basic conception remains unchanged. And their theory provides a physiological neural explanation for pain perception and ultimately revolutionized pain research. The essence of it is that A delta and type C fiber inputs open the gate and cause pain to be perceived. But by applying mechanical pressure to large diameter fibers, the A beta type, or by applying specific sound frequencies locally to the site of the pain gate closes and the pain is mediated. This is very, very good news. And of course, we know this is true partly because if we ever strike our finger or thumb with a hammer, the instinct that we have as humans is to hold that area very, very tightly. And whenever we do that, of course, the pain is massively mediated. And there is the reason that I've just explained, because of the pressure is literally, well, sound is pressure. In this case, he's literally using his own pressure of his other hand to mediate the pain. There's also the descending pain modulatory system. So there's a second system of pain mediation. The periaqueductal grey matter in the midbrain and in the rostral ventral media medulla are two important areas of the brain involved in descending inhibitory modulation. Both these centers contain high concentrations of opioid receptors and endogenous opioids, which helps explain why opioids are analgesic. Descending pathways project from the midbrain to the dorsal horn of the spinal cord and inhibit pain transmission during periods of psychological stimulation, such as strong emotions, which can be evoked by experiencing beautiful music. And there is the reason why I'm sharing this with you, of course, because beautiful music, when we are in a heightened state of joy, heightened emotional state, then that's one of the reasons why opioids are naturally created, which mediate the pain. And there is a cross-section through the spinal column showing the dorsal root ganglion, which transmits pain signals to the brain. Now we're coming on to the mechanism by which I was actually, I was helped so much in the Great Pyramid all those years ago. Breaking the pain spasm pain cycle in spinal injury by sound. It's well known that spinal injuries typically create muscle spasm to splint the cycle of the injury, providing protection while the healing process takes place. The trauma caused by a spinal injury or by other injury causes pain, which leads to muscle tension. A cascade of effects then results in which the muscle tension decreases the blood circulation, which hypothetically causes hypoxia and further pain in the affected muscles. The spasm then intensifies, which causes the hypoxia to intensify and the pain to intensify, therefore causing far more pain than the injury. And there's a nice graphic to illustrate this. And I say this hypothetically because there's very little research actually being conducted to prove what I've just stated there, but it is what I believe is the mechanism behind the assistance that I was given that day in the Great Pyramid. I believe that the healing had mostly happened actually in the 3 weeks leading up to my research trip to Egypt, but the spasm that was intensely causing such intense pain was still holding on, this splinting cycle, as I mentioned. And the low frequency sound, these are sounds from around 50 hertz that I was actually creating in the King's Chamber that day, they simply released the spasm by bringing more oxygen into the area. I'm going to come back to this question of oxygen just in a minute or two, but first the remarkable vagus nerve. And here is a very remarkable drawing showing the vagus nerve where it leaves the brainstem and then first branches off to the 2 ears. And it branches off to the tragus of the ears, actually, this little flap of tissue that overhangs our auditory canal. And this makes it extremely convenient to be able to access the vagus nerve simply by stimulating our ears with music. Ideally, of course, it can be full body immersion, but it is more optimal to use, in this case, high quality headphones to stimulate the vagus nerve. The point about the vagus nerve, of course, is that links with all of the major organs of the body. It innervates them and is a communication system going on all of the time between the organs and the brainstem. Full appreciation of the autonomic vagus nerve requires a distinction between the neurophysiologic aspects of the autonomic system's two main sub-branches, the sympathetic and the parasympathetic. These two aspects of the autonomic nervous system can be thought of as a sympathetic accelerator and a parasympathetic brake, providing bidirectional neural communication between our organs and brainstem. Several nerve tracts in the brain can send sympathetic signals to stimulate a faster heartbeat, but only the vagus nerve sends a slowing signal, achieved during exhalation. The heart beats slightly faster as we inhale and slower as we exhale, termed respiratory sinus arrhythmia, which is a measure of vagal tone. And the auditory nerve that carries sound signals from the ears to the brain receives close crosstalk from the auricular branch of the vagus nerve. I'm not going to read all of this second here. You can go through this yourself, basically, when you review these slides. But there is a hardwired connection between the nervous system and the immune system as an anti-inflammatory mechanism. Counter-regulatory mechanisms such as anti-inflammatory cytokines normally limit the acute inflammatory response and provide the spread of inflammatory mediators into the bloodstream. However, this system can become unbalanced, leading to chronic inflammation. And of course, there are millions of people all over the world suffering from chronic inflammation and the pain that goes with it, chronic pain. And there is no pharmacological pill that can be taken to mediate chronic inflammation. The best that a clinician can do is to help with the pain. So this is why sonic stimulation of the vagus nerve can help restore cytokine balance, leading to a reduction in chronic inflammation and chronic pain. We're coming close to the end now. Oxygen-driven healing by sound. So this was a research project in collaboration with Professor G of Rutgers University, who, by the way, is the father of Sayagyi. Some of you may be familiar with that gentleman, of greenmedinfo.com, probably the world's largest natural health website. Professor G that you see here came to our lab and worked with me to design a protocol in order to test the effects of music on red blood cells. And this, in essence, is the experiment. We take a vial of blood, whole blood, and we then decant it into two smaller test tubes. One test tube, as you see here, goes into the lab's incubator with a small speaker. The other test tube goes into the lab's Faraday cage, which is very, very quiet, about -25 dBA. So it's extremely quiet environment. And that's the control, obviously. What we found when we immersed music in blood, when we immersed blood in music for 20 minutes, we found a massive increase in the viability of the red blood cells. So basically, in any test tube of blood, you will always have millions of red blood cells that are alive and well, millions of red blood cells that are already dead, and also more millions that are in a kind of transitory stage between living and death. And these are the red blood cells that are, in this case, made new again by the music within 20 minutes. And the hypothesis that we began with when we discovered this, the mechanism behind it, concerned oxygen, because simply we were seeing in the Cymascope instrument, when you saw there Professor G inject whole blood into the Cymascope instrument, we actually saw that when music or sound frequencies or any frequency enter into blood, they actually imprint a beautiful pattern on the blood. And this pattern literally gave us the clue as to what the mechanism is, and it concerns oxygen. So when we receive the blood from the blood bank, it is very, very dark red, a kind of dark maroon color. But as soon as we inject any sonic frequency into the blood, it turns bright scarlet immediately. And this is telling us that the dissolved oxygen in the blood is being bound to the hemoglobin molecules and therefore turning it bright scarlet. And that was the clue. And ultimately, cutting a long story short, we were able to prove that that was the mechanism by using an oxygenation meter. And so what you will find is that any music, immersing any blood in music will cause a massive increase in oxygen availability to the proteins in the blood that will then go to work and repair the old red blood cells within 20 minutes, which is pretty astonishing. And then in much more recent times, I've been conducting experiments with white blood cells and finding an increase in viability there too, not as high as in the reds, but certainly still an increase, which in itself is, very exciting. And this work is yet to be published after we then conduct an in vivo experiment of a similar nature. And that is the end of this presentation. I hope it has helped join some dots for you and has provided inspiration for your studies and subsequent research. And I'd be very happy to take any questions if there's any time. If there's any time left, I'll just stop my screen sharing now.
Thank you so much, John. That is a really thorough trip through the physics behind all of that, and even managed to touch base with something most of us haven't thought about since doing a music degree, which is I've forgotten the name of it now. But anyway, we have some questions. Anybody have any questions? I have one that I noticed from Laura Michaels. And okay, there's a question. So we'll start with Roberta Bartasca. What kind or type of music was used in the studies?
Good question, thank you. Well, we began with classical music because both Professor G and myself I'd kind of been preconditioned, you could say, to classical music. I love classical music, and you've probably read the research where someone played rock music to a plant and it wilted, and then they played classical music to a plant and it thrived. Well, this is probably part of our preconditioning, to think that classical music was going to be the best. Actually, it turned out to provide the poorest return in terms of red blood cell count. And we now know the reason for that, which is that the classical music has a relatively poor lower bass response, basically bass register, whereas all the popular music genres that we tried, and we tried many different music genres, all of those, of course, usually have a pounding bass beat. And of course, it turns out that this bass beat is actually extremely important for healing. So who would have known that, before doing these experiments? But anyway, what happens is when you have this bass beat, it actually mimics our heartbeat, right? And in our heart, what we now know is that the heart is not just simply a pump circulating the blood around the bloodstream. It's actually also providing low frequency sound pulses which cause oxygen binding. So in other words, the oxygen that's already dissolved in the bloodstream is bound to the hemoglobin by the heartbeat sound. And here, when low frequencies from music, from popular music, penetrate into our circulatory system, it does exactly the same thing.
Right, wow. Laura Michaels has asked, there's been some research on vibration and treating osteoporosis. Are there any good references on that topic?
Yes, there are. If you download that the chapter, well, you can't download the chapter. When you download that medical ebook, you'll find in my chapter that there are references to osteoporosis. But if you write to me directly, then I'll be able to help you further with that particular aspect. I've been
Okay. And another question, actually, let me just find the anonymous attendee. What does it tell us about our own voice? Could this be considered an immunogen of some sort?
Our own voice in terms of what? Sorry, Alex, what was that?
Well, I'm not quite sure. Maybe it's with reference to what you were saying about humming.
Yes, well, certainly our own voice has many therapeutic aspects to it. Certainly, if you hum, if you close your lips and you hum, then you will beautifully excite the paranasal sinus cavities. You will create copious amounts of nitric oxide. And also, of course, those humming frequencies will stimulate your lungs, where nitric oxide is also created. In addition, humming or singing will stimulate the tragus of your ears. And that in itself will also obviously help to stimulate the vagus nerve. But in any case, the vagus nerve, when it leaves the brainstem, it branches off first, as I mentioned, to the tragus of the ears, but then it goes straight, branches next to the pharynx and the larynx. So actually, either way, whether you're making your own sound, your sound leaves your mouth and nose, ultimately stimulates your own ears, of course. But in addition to that, even the creation of your own sound directly stimulates your vagus nerve with all of the many benefits from a health perspective. So I mentioned chronic inflammation, that it balances the cytokines, but it also, many studies are showing that it slows the rate at which we age. It boosts sexual function. It has so many different benefits for us. So, vagus nerve stimulation is something extremely important for the future of medical science. It's not being focused on at all currently in medical science. And yet we now know through many excellent studies that it really should be.
Wow. Well, I would say that's a fairly robust vote. That there are immunogenic benefits, and I think that's probably what they were getting at.
Okay.
There are lots more questions coming in. Talking about music, the mix and different frequencies of sound and noise, what do you think this will do to the body systems? Well, I think you've given quite a lot of information on that. I don't know.
Well, just very, very briefly, again, if you read that chapter, you will find the chapter that I wrote in the new medical textbook, that most of the healing frequencies are in the kind of lower registers. Most of them are, not all, but many of them are under 100 hertz, let's say, and for good reason. I've already mentioned one of the many mechanisms that are at work because of low frequencies. This is the increasing the availability of oxygen in the body, but there are actually many other biological mechanisms that are stimulated specifically by low frequencies. So I think read that chapter and all will become clear for sure.
Great. Okay. Just to remind, Leonardo, do you want to do that reminder? Signing up for the newsletter. I think there was someone's put one in there, or maybe it wasn't you that put it in there. Have we got time for another? I can't hear you, Leonardo. Have we got another question? Interesting sound for preterm infants. Your research seems very relevant, but is it known and therefore not utilized in the UK? Okay, so using some sort of sound therapy for preterm infants. I don't know for what specifically, but is there, and it's a question about whether it's not very known about in the UK.
Yes, well, not just the UK, but the whole world, basically. So, one of my roles in the future, well, now and in the future, is to help educate. Of course, this is why I'm, very happy to be with you all today. But really, medical science has a lot to catch up on.
Yeah.
And a colleague of mine, Dr. Shamini Jain, mentioned to me recently that there's a 17-year gap between new medical research and this medical research being, uptaken by the medical community, which is shocking, really shocking. However, just coming back to your point, about sound therapy, for example, and music medicine. Music medicine is actually a new clinical term, which is good news. So, many clinicians are now recognizing that music, amazingly, has therapeutic potential. Even without a therapist being present, music does have therapeutic potential, does have physiological effects, of course. But in general, music medicine is not being used worldwide yet. I think it will come. And sound therapy is, well, definitely not being used in hospitals, excepting a few studies are showing whole body vibration is useful. And that question that was mentioned earlier about osteoporosis, for example, very low frequency whole body vibration is great for stimulation of the skeleton, the bone structure of the body. But yeah, it's a huge gap currently that needs to be, well, I'm trying to bridge this gap between mainstream medicine and integrative medicine right now. I'm trying to do that in every way that I can.
Brilliant. It needs an army of people.
It does indeed.
It's happen, yeah. I think we can share the other questions with you, or we can do them now. What?
I'm happy to continue if you wish to, but I'm
Yeah,
equally
there's
take
still
any questions in writing as well.
So the more, let's see. Do you have any thoughts on the therapeutic potential of noise with certain spectral characteristics, for example, white noise? In other words, do we really need music, or is a particular mix of frequencies not necessarily harmonious enough? That's an interesting question. Yeah.
What a great question. Do we really need music? Well, the answer is yes, of course we need music. But let's come back to your question first about sound, in particular white noise rather. Yes, white noise is extremely healing. One of the reasons for this, and I must say, I must give a caveat to this, that we are talking about white noise, which is in a kind of Goldilocks zone of pressure levels, sound pressure levels of between 70 dBA and 85 dBA. We don't want the sound level to ever go above 85. And we certainly don't want it to dip below 70 because Professor G and I did a lot of experiments with white noise and blood, and we found that below 70, there's very little therapeutic effect on the blood. And above, well, actually, we did an experiment with 110 dBA, and it killed all of the red blood cells within 20 minutes, completely dead, all of them. So, we've got to say this is very important to get the right sound level. Sources of white noise in nature, such as waterfalls, the ocean waves, and so on, all extremely healing, and they never get above 85, well, maybe 90 dBA if you're standing very close to a waterfall. But essentially, we must not go above 85 because that will stress the cells in your body instead of helping them. We talked about sonocytology and James Jimzewski's work. What happens is, when cells are challenged in some way, as I mentioned, they need energy in some way, and sonic energy is equal in many instances to nutritional energy. So provided you provide a very broad spectrum of sound to the body that's not above 85 dBA, then the cells will simply take from that soundscape whatever frequencies they need and simply reject the frequencies gently that they don't need. And another source of white noise is the gong. The gong is a wonderful healing instrument, again, provided it's played at moderate sound levels and not too high. Because anyway, getting back to James Jimzewski, no one has currently conducted the research to know exactly what type of cells in your body produce what type of complex song, right? So how do we help them? Well, we help them by giving them a complex sound field, whether it be from noise or from music. But of course, music also has other many benefits, such as I mentioned in this little presentation. It produces happiness in us. White noise doesn't do that, but music does produce happiness, joy, dopamine is created, cortisol is suppressed, and all the many other mechanisms that occur because we're immersed in a musical environment.
Mhm. Great. Yes, that really helped to make that distinction. Kate Jones asks, so music has been used for healing throughout time. I wonder if there are some historical examples that bear out in this current science. Hmm.
I don't,
Um,
I don't think
yeah,
that's the
no, I
question.
think it's a question about how music is used in healing today, perhaps compared with the other historical examples.
Okay, well, from a historic viewpoint, my own research was actually inspired by Pythagoras of Samos, who, round about 500 BCE, he was the first guy in history, as far as we know, to actually uh, to show the correlation between music and healing. Certainly, the Egyptians, he visited Egypt with several sources, good, reliable sources showing that Pythagoras visited Egypt several times, and it's almost certain that he gained a lot of his knowledge from the ancient Egyptians, although there's nothing written extant, to prove that, but simply the fact that at the point when Pythagoras had visited Egypt, the Egyptians had been making music for like nearly 3,000 years before Pythagoras's visit. So the idea that they didn't get information from the ancient Egyptians is pretty, not likely anyway. So also, of course, there are many other instances of use of music as a therapeutic agent. For example, the Vedic tradition, they were using mantras going back many thousands of years, prescriptive mantras. And of course, what's a mantra if it's not using vocal sound? And I've already, mentioned some of the many mechanisms that occur when we vocalize. And so it's quite obvious to me why their system worked.
Right, that's what she's getting at with this
Yeah,
question. It was saying, does the current scientific evidence support those
it
much,
does.
much
It
things?
does. Absolutely. 100%.
Yeah, yeah. And Natalia Pavliuk. Now I understand why my piano students with refugee war trauma background love playing those heavy octaves in lower register. They're literally drawn to the heavier bass sounds in classical music as well. Hmm.
Wow. I'm really glad that you brought up this question about piano sounds, or this point about piano sounds, because of course the piano has a beautiful range. I mean, 88 notes, of course, but of course every piano string, as they're called, and not just one string, they are groups of strings, usually in threes, and the numbers of frequencies created by piano music is just phenomenal. I mean, like 10 harmonics is is nothing compared with what we see sometimes from pianos. It's just astonishing, the range of frequencies. And we have a friend in Dan Kohler in Florida, who is actually a really excellent piano technician, and he brings people to his home to heal by lying under the piano while the piano is played via one of those automatic piano player devices, and people are reporting all sorts of amazing healings from so many different illnesses. So, I think the piano is a wonderful healing instrument.
That does remind me, just anecdotally, of a colleague in Padua, in Italy, who plays the didgeridoo, and I think he was trying to convey something of how they use those in a similar way, and he asked me to lie down on the floor while he played the didgeridoo over my stomach, and I wasn't sure if he was winding me up or I missed the point.
No, no, because a didge is actually another wonderful healing instrument, and of course that has a tradition going back. Well, some people say up to 40,000 years, but
Right.
I don't know about that. But unfortunately, again, a little bit like the Pythagorean thing and the Egyptian thing. There's very little written, in terms of, well, actually, there's nothing written from the Aboriginals themselves, but there's a lot of anecdotal, writings on the subject. Broken bones are healed, all sorts of maladies are healed by
Yeah.
the, and the reason is because again, it has a very broad spectrum of frequencies. I looked at it on our lab spectrum analyzer a few months ago, and it covered literally the whole of the spectrum, right from 12 hertz up to 32.5 kilohertz, and no doubt way beyond 32.5K. You know, in other words, it has a fabulous spectrum of frequencies. So again, coming back to this point, that if you're immersed in a very complex sound field, your cells will take what they need from it to energize themselves, you know.
Amazing. I think that's a great point to leave it. But I'm sure we could go on.
Sure. If anyone else has questions, you know, please send them in. I'd be very happy. I'm not saying I'm going to do it literally tomorrow, but you know, as soon as I can, I will answer your questions in writing to Alex.
Yeah, and I think some people are asking about how they can access the recording of this and the PowerPoint. So, Leonardo, will you convey that information? You've got no microphone, but we will. There you go.
All right. Yeah. Thank you very much, John. Fascinating. And thanks for the Q&As, everyone. Thank you for being here. Once again, I'm putting the newsletter link in the chat so you can have access to the PDFs of the lecture, this recording, and a short introduction to it, as well as probably the answers of that you'll send over, John, once you have the time to answer those written form questions. So thank you so much.
There are lots and lots of messages of appreciation. I think this is such a new world, really, for all of us. So thank you so much, John, and I look forward certainly to reading some of the literature that you've cited today.
It was a great pleasure, you know, and I'm sorry it was a little bit rushed. I was really just trying to squeeze in as much as possible in that short time.
Yes.
But you know, it's great if you have the slides, then you can review them at your leisure. And I think that, you know, everyone that looks at the slides and reads them carefully will actually gain quite a lot from them.
Absolutely, yeah. Brilliant. Thank you so much. And speedy outputs from your research, as you say, that's what we need. The 17-year wait is too long.
We need to narrow that gap a long way, for sure.
Yeah, okay.
Many blessings. Right. Thank you so much, all Alex. Thank you, Leonardo.
Okay. Thank you. Thank you so much. See you soon.
Bye, everyone. Bye.